Endocrine responses to stress. So, what do we mean by stress? Well, anything that is life threatening is going to stimulate the stress response. Infection will cause a big stress response. Um, Fever is a large sympathetic drive, which is a large stress response. Trauma will evoke it. Large blood loss, but also anything real or imagined that evokes a strong negative psychological response will generate some kind of the stress response, some level of it. Whether that be running away from a bear or an exam you don't feel prepared for, you're going to get some kind of sympathetic drive going. And this will mobilize substrate. And the difference between this and exercise is that you will mobilize substrate and perhaps not even use it. Whereas exercise, you're kind of demanding that energy be made available. Here, energy is sort of made in anticipation or because of the stressor that's been imposed on your body. And so you're going to get sympathetic activation and the release of epinephrine and glucagon. And this is going to inhibit insulin release. And so you're going to get glycogenolysis and stimulated by epinephrine and glucagon, lipolysis, and reduction of triglyceride synthesis. And then on the other side, your hypothalamus will secrete corticotrophin releasing hormone to adrenocorticotrophin hormone, which then will raise your cortisol levels, and this is going to stimulate lipolysis, also reinforcing epinephrine and glucagon, but also increasing proteolysis, or bringing a third substrate to bear, substrate storage, and this will also encourage gluconeogenesis, and that will increase plasma glucose levels. And so there's a lot of substrate available for you to have during the stressful time. And so the stress response is an integration of the sympathetic system and the hypothalamus pituitary adrenal axis. And so local injury, for example, would cause an immune response, and the cytokines as a danger signal would then activate stress signals. And then the cortex and the limbic system is going to fire norepinephrine adrenergic neurons, arouse your behavior. On the other side, you have CRH releasing ACTH from the pituitary, and then you get a rise in cortisol. Cortisol is then permissive for more epinephrine, so that enhances the sympathetic systemic response, and you get mobilization of energy and redistribution of your cardiovascular energy, so vasoconstriction in areas that are not metabolically active. Cortisol has a central function in the stress response. It's permissive for epinephrine, but it also inhibits many areas. You obviously have the feedback loop of cortisol dampening its own release, but it's involved in shutting down reproductive functions, feeding sexual activity, and just your general arousal is more aggressive. But it also has a large role in stemming the inflammation. One of its critical functions is to make sure that you don't have an overzealous immune response during the time of stress. Catecholamines, they work by vasoconstriction, which is good in hypovolemia. They raise blood glucose, that's great for hypoglycemia, and they enhance your metabolic rate, which is great for hypothermia. So this is just a revision of the slide of the central role of catecholamines in stress. And just to further point out, the epinephrine is more of a hormone that is just released in the blood and has a systemic function, whereas norepinephrine is more neurotransmitter-like, where it's released on target cells. And so this shows you more in depth of where cortisol has its anti-inflammatory functions. I mean, glucocorticoids are used clinically all the time to suppress wayward immune reactions, and that's because that's exactly what cortisol does in the body. You know, the inhibition of platelet activating factor and nitric oxide, its inhibition of formation of arachidonic acid can lead to less prostaglandins, lower leukotrienes, and this will dampen the neutrophil response, so less invasive leukocytes into a site of injury. It inhibits macrophage function by preventing cytokine release, which can dampen fever, and then the T cell response, which can knock on into B cell proliferation and antibody production, is also dampened. So it has a general wide effect on the immune system to suppress its function. And it's critical then in this negative feedback of the immune response. So you get your stressor, which will invoke an immune response. You get cytokine production, and that will stimulate cortisol release, which then will feed back onto the immune system. Another example of negative feedback. So this graph is showing how a sustained stressor will raise blood glucose levels. The stressor this time is hypoxia. The patients are exposed to it for tens of minutes, and blood glucose rapidly rises to about three times the original level, and concurrently with that you get a rising glucagon, which is likely contributing to this increase in blood glucose. A summary of what the different roles of the hormones are in the stress response. Epinephrine reinforces the sympathetic nervous system, mobilizes carbohydrate and fat energy, and increases blood glucose levels. Cortisol and the hypothalamus pituitary adrenal axis mobilizes energy stores, reinforces the epinephrine response, and stimulates proteolysis, and so it increases blood glucose, amino acids, and fatty acids. Glucagon increases blood glucose, insulin goes away, it's inhibited during the stress response. And then you have another adrenal gland hormone that's not involved in metabolism, but is involved and important in the stress response because it regulates systemic blood volume. And that's the renin-angiotensin aldosterone system, and then vasopressin being released from the posterior pituitary is also increased in the stress response, and this also helps regulate blood volume by vasoconstriction and fluid retention. So this is just a reminder of how the catecholamines are synthesized. From tyrosine, norepinephrine is converted into epinephrine by phenylethanolaline N-methyltransferase, and this is increased by cortisol, and so cortisol is permissive for epinephrine release and potentiates its release. This is the aldosterone system of fluid balance. So with hemorrhage, you get a loss of extracellular fluid volume, and the renal juxtamedullary cells, they're going to sense this drop in pressure in blood volume, and they're going to release renin. And the renin stimulates the formation of angiotensin 1 from angiotensinogen, and then that's converted to angiotensin 2, and that'll stimulate the adrenal gland to produce aldosterone, which will retain sodium and maintain blood volume. And this is antagonized by atrial natriuretic hormone from the heart, and so the balance between sort of the aldosterone and the ANP will regulate your fluid volumes during stress.